So we hope.
Well, it seems to be holding it.
There you go.
Yeah, that's the thing.
That was a fantastic idea. So let's hope that holds.
Thanks.
I'm either going to just give it to Tom and have him do something about it, or just...
Okay. We're going to try that. Welcome back to Stellar Spectroscopy Central. Let's see, we've got assignments, and I thank you very much. I will try to have those back to you shortly. You know, hope you felt I've been keeping a good pace in returning them. I would like to hand out another assignment on Thursday, and mostly what I want to do is get us to the multi-electron atom so we can get to the punchline eventually. And I think that it will be smart for me to go back to handwritten notes after this. This was an experiment to see how it worked. I am all about your feedback, and I would like to continue to have the feedback because I will adjust for it so that you can have the best success in the class that you can. So please tell me if you have thoughts about it. Please, please. I can't change if I don't hear from you, but I don't have these in handwritten form. I think what I'll do in the future is I will adjust them so that I can take the relevant parts and consolidate them down into that handwritten form. It'll be a lot better. It took me a whole summer to get these ideas down in the first place. Okay, so last time we met our superhero, the atomic environment, we had talked about natural broadening, okay? But I just want to again remind you of this very complex spectrum of hydrogen and all these energy levels. In your homework assignment, you only did the Dirac atom, and remind you that in fact the S1 half and the P1 half actually are not energy degenerate as you did in your homework assignment, and so that a little transition here is possible called the Lamb transition, okay? And also that these 7 transitions of H alpha are actually all unique energy transitions now, that none of them are degenerate. Remember, in the Dirac atom, there are 5 unique transitions in terms of energy, and 2 that had the same energy. So you would only see 5 lines for H alpha in the Dirac model, but we knew that we measured 7, we need more physics, that's when we put in the radiative corrections. And we talked about the relative strength of those transitions based upon the multiplicity of states being summed up over all those states, and the dipole moments of the overlap integrals. So here was the spectrum, again showing the doublet of Lyman alpha, the doublet of Lyman beta, and the multiplet of H alpha. And then we talked a little bit about free Brown, and then we said, okay, let's talk about natural broadening. We talked about how the energy width of one of those energy states was related to the Einstein A coefficient, because that 2 over the A coefficient was the E folding time for that transition to happen. Decay of the wave function. We came up with this picture here, so that now we don't have a unique energy photon that would come in or be emitted, but there's a range based upon this distribution. And what was the name of that function? Anybody? Does anyone remember the shape of that function?
Lorentzian?
Lorentzian, correct. And we said that the width of the wavelength fractional spread, in other words, the full width half max of that thing, roughly is about 10 to the minus 7 angstroms, and roughly about a fractional frequency is also around 10 to the minus 7. But in angstroms, the width is around 10 to the minus 4. Very narrow broadening in the range of photons, energies of the photons, wavelengths of the photons. Okay, we went through the decay of the time-dependent Schrodinger function, and we talked about how do we determine the width of these energy states. we said that, well, to get the width, we have to know where, from say this stage to this stage, to get the width of that transition, or the broadening of the line, that we needed to know all the channels that the upper state could decay to, and we needed to know all the channels that the lower state could decay to. We then summed up the A coefficients of each of these transitions to get the total E folding time or width of this one, and then we summed up the A's for the downward of the lower transition, and then we summed those two widths to get the entire width of the function. Okay, so that's what these equations are telling you. You have to sum over the lower L states and over the higher L states, because you are subject to, for this one, these are the L-1 states, and these are the L+1 states. For this one, there are no L-1 states, there are only L+1 transitions. So there's two separate sums, one for the L-1, one for the L+1. Okay. So when you go to the tables and you look up a transition, you will see something called gamma for that transition on these tables. That is the sum of the gammas for the E-folding times within a factor of 2 of the upper and lower states. Okay, and then that is, turns out, after we did the Fourier transform, got the power spectrum, we came up with the fact that this is a Lorentzian. And here's the shape of the function. Let me write it down for you. Very famous. We call it phi. Okay. And it basically is equal to 1 over pi. And then a quantity up here, which is gamma, over 4 pi, divided by nu minus nu 0 squared, plus the quantity gamma over 4 pi squared. Okay, and so the width, this the width of this is given by this quantity, and the height is pi over this quantity, pi over that quantity. Okay, so it's normalized to unity area, and the idea was that the wings of the Lorentzian are much broader than the wings of the Gaussian, shown in the dotted line there. Okay, so that's where we ended last time. All right. Now, if you, it really upsets me that this pen is a piece of crap, because this is not going to show up on the video. Is that better? This is if you do it in frequency space. And how many people have seen this before? Okay then. Learning new stuff, I love it. Well, it's very possible that you're going to see it again, and it's very possible that when you see it, nobody's going to explain to you where it came from. So now I think at least you know that, hey, you know what? All these things come from the wave functions, okay? And the probabilities, which is the Born, the Born rules. Function that looks like that. That's mu naught, and this width here is the gamma over 4 pi. All right. And if you turn it into wavelength, well, apparently I don't do that yet. This is what it looks like in frequency space. Okay, this is the peak. Notice when nu equals nu naught, this is 0. Okay, so when this becomes 0, then you're just left with this over this squared, which gives you the 1 over pi, blah, blah, blah. Gives you the amplitude of 1 pi over y. And then as you go out, this goes, it's very Gaussian in the core, and then as you get to very large nu minus nu naught out here, you can see that it goes as the inverse square of the difference. So it starts to go as the inverse square out here at large distances. Okay, just a good old functional analysis there for you. Okay, now We have emission lines in astronomy, and we have absorption lines in astronomy. This is a class about stellar spectra, so it's mostly going to be about absorption lines. And you'll remember from the beginning of the class, I talked about something called the cross-section. Now, I haven't talked to you about cross-sections in the atomic physics stuff, so today I want to mention that. Okay. Now, if you're going to study galaxy spectra, they're going to have emission lines in them. You're going to, from the gas. How do you connect the emission line to the atomic physics? And so that's what I want to talk about real quick. It's the bound emission and the absorption cross-section. Okay. This here is the original formula, repeated, of the Einstein A coefficient, some constants, the transition frequency, and then the overlap integral, which is the dipole moment of the two wave functions. Okay, remember that's the overlap integral. Okay, so this is where the wave functions come in. Okay. If you rewrote that, if you write it out, you get all this complicated stuff, and then if you do the integral of the wave functions, which was way back when, you actually can get out a very nice little formula, say for the Lyman series emission lines. Okay, A10 to AN1. So basically, N equals 1, L equals 0. That's the 1, 0. Filed appropriately. So here's the N equals 1, L equals 0, or S state. And then you have, not drawing all the other ones, of course. Here's N prime equals 1, L prime, L prime equals 1, N prime equals 2, N prime equals 3, L prime equals 1, etc. These are the, here's your Lyman alpha, here's your Lyman beta, here's your Lyman gamma. Okay, so this is the formula for that. The 1, 0 is this state, N equals 1, L equals 0, and the N1 is the fact that these are all L equals 1, and then N could be 2 or 3 or 4. So as a function of N, put in N equals 2 for Lyman alpha, put in N equals 3 for Lyman beta, etc. You get the A coefficient, okay, straight out of the overlap integral in terms of just N. And I just wanted to show you that it has this nice close form and tells you the N behavior. Okay. All right. Now, once you have the A coefficient, that gives you the rate at which a transition would happen spontaneously in a single atom. Let me repeat that for you. What does A give you? A gives you the rate, inverse seconds, in one atom for the E-folding time of a transition to go from, say, N something to 1, 0 or something like that. Okay, so from upper to lower transition, the A coefficient for that gives you inverse seconds, the rate that's going to happen in a single atom for a given atom. So how do you get out the intensity of the light that would be coming at you given that information for one atom? Okay? And it's easy.
Can we zoom in on that a little bit more?
Yes, you can. I'd be happy to.
That's better.
Yeah, you know what? I should have been doing that all along. I don't need to have it any smaller than that. I don't care about all this math, folks. What do I care about? Okay. Like, first of all, it's right here. The power emitted is the rate times the emitted energy. What's the emitted energy? H nu, the photon that comes out. So the power emitted is H nu times A. That's the energy emitted. Okay. Now you want to do it over all solid angle. Okay? You want to normalize it because this is the energy coming out over all solid angles. How many? But you're going to be talking about a line of sight that you're looking at. So you want to normalize out the energy that's going out into all solid angles into your path. So how do you do that? There's 4 pi solid angles, so you normalize them out. Okay. Now, we've made an assumption here. We've made an assumption that the power is emitted isotropically. Otherwise, we have to do integrals over phi and theta, and it's more complicated. But if it's isotropically emitted, the energy emitted isotropically is the energy per unit time, right? That's the power output per steradian. Okay. Now that is all of the power emitted. But if we want the power at each frequency, all we have to do now is multiply by the line broadening function. And there you have it, ladies and gentlemen. The emission per unit steradian, energy per unit time per hertz. Let's look at this. This is steradian to the -1. This is erg. This is second to the -1. And this is hertz to the -1. You're used to seeing it like this. Okay. The energy per unit time, per unit solid angle, per unit frequency. That's the flux density. Well, almost the flux density. We don't have the centimeters in there yet. We can't do that until we get a telescope and we measure it, and we have to be a certain distance away from it. But did you see how easy that was? Renee's going to be talking about this in the ISM right there. What are you laughing about?
Just thinking of Renee talking about Einstein coefficients. Just nothing, it's fine.
Is Renee talking about these things?
No, it just, we would joke about how much she loved Einstein coefficients.
Oh, I see.
So it's like,
Inside joke with Renee. I like inside jokes. Okay, so I've obviously got it more complicated to talking about transition from NL to N prime L prime. Okay, now this phi is given by this function, right? So then, just writing that out, h nu over 4 pi Einstein A times phi. That gives you a function that is identical to the shape of the line broadening function, but has an intensity h nu A over 4 pi. Okay, and that's how you get the line intensity out. Now, we're eventually going to have to put that into some radiative transfer. Now, if you want the energy in the whole line, what do you have to integrate over? I must be deaf.
What was the question?
Repeat the question. If you want the entire energy in the line, or I should say the power in the line, what do you have to integrate over? Frequency. You integrate under the curve. Okay. Now, if you've been paying attention, I said that when you integrated this, it's normalized by definition that when you integrate it over all frequency, it's 1. Okay. So, if you, I wanted to say that if you want to replace, I didn't say this before, but if you want to replace A with the oscillator strength, which is what you'll see if you look up the tables in the book, you'll get this number. It's basically you just substitute the definition and you get 2 pi e squared and masses and the nu squared instead of nu times oscillator strength times the broadening function. Okay. So it's same exact equation, just written in terms of Einstein A or written in terms of the oscillator strength. Now, if you want the full energy per second, the power per unit solid angle, you integrate over all frequencies. Now, since this is very, very narrow, on the order of 10 to the minus 7 in width compared to the value of nu, you can go ahead and pull h nu out of the integral. Only because it's extremely narrow. If it was a very broad function, obviously you're integrating over nu, you can't pull out nu. But if it's a Gossamer thin function with, 10 million parts of 1 is the width. So anyway, the integral over all nu of this function is 1, and you basically just get that for the entire power per unit steradian. The units of that, of J nu, is power per steradian. So when you're doing some astronomy and you need to know what the line intensity is, you got to know the Einstein A, or the oscillator strength, and some constants, and you put it together and you can pull it out. Okay. Now what you'll do is you'll integrate and get some kind of thing like an equivalent width or whatever, and you have to convert this to flux in order to get the right answers. But what we really want to talk about here is bound absorption and introduce to you where the cross section really comes from. Okay, very important. Okay. Well, let's repeat this now, but let's do it for absorption. Okay. All right. We're going to define a coefficient for absorption. It's going to be the absorption power per unit frequency per unit solid angle. We had J nu for the power emitted per solid angle per unit frequency emitted. For absorption, we're going to use K nu. Same units. All right, so to do that, we have to take the rate, again, in inverse seconds and multiply it by the energy to get the power. And if you remember the definition of the rate, it was 4 pi B times the intensity of the energy coming in. That was back on the definition of the Einstein B coefficient. That if you took 4 pi, okay. So you now multiply this by h nu. So you start with K nu equals h nu times B times I, h nu times 4 pi B times I nu. That gives you the energy per second, okay? You want it per steradian, so you have to divide by 4 pi. Reduces it to that, okay? But you also need to remember to throw in the function nu. Okay. So now you get an absorption profile. Okay, kappa nu, K nu, kappa nu, which is the energy per second per steradian per hertz absorbed out of some I nu. Everybody see that? So I nu is some number here. It actually could be frequency dependent. I nu could actually do this, and then your absorption could be a Lorentzian like that. The shape of which is defined by this, the magnitude of that drip is defined by that.
Or is B the black body intensity?
I knew could be a black body intensity, for example.
What is B?
Oh, B is the Einstein B coefficient. Apologize if I glossed over that too fast. In this case, you need the Einstein coefficient for absorption. And the rate at which absorption happens depends upon the intensity of the incoming beam, because the intensity of the beam is what feeds you the photon rate, okay, the power rate, and then 4 pi times B. So basically, here's what you have. Right? Okay. Now, what we want to do is rewrite this in terms of the oscillator strength. Okay. So when we do this, I'm not going to go back to it because it's pages back there. There was a relationship between A and B, equation 2.12, if you remember. They have like an 8 pi nu squared over hc, kind of factor in it. Okay. So then you can account for rewriting A and B in terms of each other. Okay. And then if you take the equation for the oscillator strength in terms of the spontaneous emission, okay, a lot of those constants cancel out, and you're left with pi e squared over mc times the oscillator strength. And you might be wondering, where does this G or GNL over GNL prime come from? And that has to do with the multiplicity of states. Okay. When you switch from spontaneous decay, you're going from higher multiplicity states to lower. When you're doing absorption, you're going from lower multiplicity states to higher. So the rate of absorption can be greater than that of emission. So you have to have a ratio of the multiplicity of states. That also came from, maybe I should go back to it. Okay. Remember, there was a relationship between the Einstein spontaneous emission and the induced emission. Okay. And I believe it was something like A equals 8 pi nu squared over h bar c, or I can't remember that constant. Okay, that doesn't matter. Times the B for spontaneous emission. Okay, but the relationship between the B of spontaneous emission and the B of absorption was the ratio of the G of the upper state, lower state to the upper state. Okay, I hope I've got that right. So basically what we've done is we said, oh, this equals that. So there you get your G's and your B absorption, and then you take your A, substitute it into the equation for the oscillator strength, you end up with this. It's very simple. Did I do that justice now to see so you can see where it came from in principle? You can do the math yourself. I'm not a stickler for giving you a homework assignment for that. Okay. Anyway, you end up here now with the expression for the absorption coefficient, pi e squared, oscillator strength. Notice that you have to know the photon field coming in, and then you have the broadening function due to the uncertainty in the energy states of the upper and lower levels. Okay. How do you get the cross section? The cross section is defined right here. Cross section, centimeters squared per unit frequency, is the absorption power coefficient divided by the intensity of the photons. In other words, you're normalizing out the intensity of the incoming beam. Remember, the definition was the power removed from the beam divided by the flux of the beam. When you do that, it's basically the same equation as above, but you've taken out I nu. Okay? And so you finally get now, if you insert this equation for phi, you get the absorption cross-section. So now you see where it comes from? Absorption cross-section. Okay. So what do you get? You get sigma nu, which is centimeter squared per hertz per atom. In other words, it's for a given atom, and it's per unit frequency. This is just equal to pi e squared over mc times the oscillator strength times 1 over pi gamma over 4 pi nu minus nu naught squared plus.
Is E the number E, or is it?
This is the
Charge.
charge of the electron. Great question. What I try to do for my notes in the book is write the exponential as exp. I always, in all my equations, write it that way. And the reason why is, guess what? When I was studying this stuff, really for out of class for the first time, I was studying it out of a book called AGN squared, Active Galactic Nuclei, or something like that. And it was from a guy named Osterbrock, who was a giant in the field, and he wrote an E. I thought it was the exponent, not the charge on an electron, and I spent a month. Why am I getting this all wrong? Why can't I get it right? Where's the, and it was that E. So from now on, whenever I write notes, or write a paper, or in a chapter, I write exp function, because it just is a bad memory.
What is F?
F is the oscillator strength. Okay, so F is the oscillator strength, E is the charge of the electron, this is the reduced mass of the electron, okay, from our initial definitions, speed of light. This is the damping coefficient, constant, that we derived, okay, and so this gives you the shape of the function here. And this tells you that the cross section, remember before I showed you the cross section had a shape to it, and it has an amplitude to it. See, the amplitude comes now out of this physical constants, the gamma function, and the oscillator strength, which is related to the Einstein A, which is related to the overlap integrals. Okay. So basically, then if you want to convert it to wavelength, you use this relationship here, you go through the math, and you get a very, very similar equation in terms of wavelength. If you want to plug that into your code to make an absorption line, okay. What'll happen if you go and you want to know, well, what constants do I put into these equations when I use them? You probably are going to go to a spectroscopic site like NIST, National Institute of Standards and Technology, and look up lines, and it's going to say, oh, Lyman alpha, the Einstein A coefficient is yak, the oscillator strength is yak, the gamma coefficient is yak, and there you are. You pluck them out, you stick them into your equations, and off you go. And then you can model your lines. Okay. Now what did we learn? We learned that in a spectrum, we were using alpha before because eventually we're going to convolve this cross section with some distribution, redistribution functions, but if I just do it in terms of atomic physics, okay, so now you know where that cross section comes from in gory detail, right? Okay. This is basically, you have the energy coming in per second per straightening per hertz in your line of sight. Once you calculate that, you then divide that by the incoming intensity. That gives you the cross section. It's functional form with nu, okay? And then the measured spectrum is e to the minus column density times that cross section. So now you know, we started out the class with that equation, but you didn't know really where that cross section came from. Now you know where that cross section came from. even if you only understood 5% of what we've talked about here, I still think the general framework has made its way to you, right? It's like you've got the frame, you've got the picture, some parts of the picture really pulled focus for you, some parts of the picture are really blurry still, but the fact is you now understand there's a painting there, you know, and I should stop my analogy there. Okay. So that's what I intended to do, was provide you that framework. And ultimately, again, I'll show this plot one more time. This is the Lorentzian for Lyman alpha transition, the shape of it given by the cross-section dependence here, the amplitude given by pi e squared over mc times the oscillator strength. Here it is, in units of 10 to the minus 11 centimeters squared. This is in per unit angstrom for a given atom. Okay. Here's the transition, 6701, 1215.6701. Here is delta lambda, this is units of 10 to the minus 4. So this is 6702, this is 6700. They're very thin, very small. I mean, you could not resolve this in a modern day spectrograph, really. Okay, and that's the cross section, and it goes in there. And then if you know the column density of atoms, which was the integral of the density times the path length, boom, you're done. Okay, so if you've got an absorption line and you want to, what is it you really don't know? You measure this in the spectrum, right? There it is. There's a spectrum. Measure an absorption line. Okay, measure an absorption line. Boom, there she is. What do I do? What do I know? If it happens to just be no thermal motions or anything like that, the only physics I'm going to account for is the physics of the atom and the uncertainties of the energy levels. The shape of this is the shape of that put through the exponent. What I don't know is this. I can get the atomic constants and get that and get this amplitude. Then I can fit this with a model line and I adjust n until the data matches the observations. I get n, and n is the column density. It's the integral of the density and the path length. So I don't know the size of the cloud, I don't know the density of the cloud, but I do know the product of that. And that's what you get out of a spectrum. Okay? And then it turns from out, you know, how many people went to the pizza lunch and saw that they're getting out abundances? Okay? Abundances are effectively relative densities of different chemical elements. Remember that this, in this case, if this is a Lyman alpha line, this column density is only the column density of neutral hydrogen in the ground state, if that's a Lyman alpha transition. If it was an H alpha transition, what would it be of? Neutral hydrogen in the Balmer state, equals 2. I'd be missing all the neutral hydrogens, I'd be missing all the hydrogens. Okay. I'd have to go find a Paschen series transition out here to find out those, and I'd have to go and get in the UV and get a Lyman transition. You know, you can't get it all at once. Turns out, what if you don't have infrared spectra and you can't figure out how many Paschen states there are of hydrogen? What would you do? You'd get your handy dandy computer out and you would model the gas physics. Kind of like we're going to do for some of the homework problems. Yipe. Okay, I'm going to have you calculate the balances of hydrogens in the Balmer states and in the ground states and in the Paschen states, and not how many are ionized compared to how many are not. Those relative densities are the densities that go into the integrals for that given absorption line. So we want to bring that back home to you. This is not the column density of all the gas. So you have to measure many, many absorption lines from different many chemical elements. You get the densities of, say, I've got the column density of ionized calcium, and I've got the ionized of neutral sodium, and I've got the column density of, say, singly ionized nickel, and I've got the column density of singly ionized iron, and I've got the column density of, say, Balmer state hydrogen. And that's what you have. How do you then get a metallicity out of it? Okay. You have to model the gas. You have to model the gas such that you get out the column densities you measured. And once you get all those adjusted so they all are consistent with your data, then you assume that the column densities of the other things, or the densities of the other things, are in the right proportions, and you say, there's my gas model. My metal, and I've got so much, iron in there compared to hydrogen to make this all work, and therefore my Fe over H is blah in my star. So, remember they were talking about modeling the metallicities and the offsets, and we have a pipeline, we got 7 different codes that do it, right? It's tricky business. How many of you realized that it wasn't a direct measurement, that you had to actually model the gas physics in order to get that metallicity out, right? I know. This is the day and age of watch, don't raise your hand. I'm still getting blank stares. I got one in the back. I got someone scratching their head a little bit going, I don't know, maybe I'm going to fess up here. But the rest of you, nope, not going to play your game, Chris. All right, good enough. Now remember this bound free. Remember the Balmer edge? Okay. That Balmer edge is extremely important whether you're studying stars or whether you're studying galaxies, because what are galaxies? Mostly in terms of absorbed light, it's a composite spectrum of billions of stars. Did anybody catch the irony? It's like in that talk, oh, we're going to have the spectra of 1 billion stars. And I thought to myself, that's still only 1% of the galaxy. That blew my mind. Because it sounds like, wow, we got most of them. But this was the cross section, which doesn't have this shape, okay, due to the ionization of neutral hydrogen. And this, in this case, is the n equals 1 to state IK, where K equals infinity and K equals 0. Okay. Remember, K is the quantum number related to the kinetic energy, and the bigger K is, if K is infinity, the kinetic energy is 0. So that's the threshold. Okay. All right. 10 to the 6 has a peak of 6.03 times 10 to the minus 18, and this shape that sort of goes as the cube of the wavelength. Where did that come from? Okay. Same place. Okay. If you start with our definition of the cross-section, you just have to account for the differential change in K with nu, which comes from the simple relationship 1/2 mv squared we have this relationship. But that's also going to be equal to h nu. Okay, so you can get a relationship between nu and K. Okay, and basically you plug that into the oscillator strength that we had, and you get this very nasty relationship for the cross section. And I just wanted to show this to you, Because again, what's going to happen in every book you read, you're going to see that. And that's what you're going to see, and nobody's going to explain a single thing more to you. You go to what's it called? Ribicki and Lightman? Yeah. Okay, you go to Bob. If you go to anybody except for Osterbrock, they're going to say, it's 6.03 and it goes as the inverse of nu cubed, or it goes as lambda cubed, and that's that. Boom, done. Okay, there's your physics. Well, guess what, folks? I got news for you. If you want to do this for real as a pro, you can't use that equation. But that's the only freaking equation you're going to see in every damn book you get. And then you're going to wonder how people are doing this science with an equation that's just wrong. Okay? Because it really looks like this. And that's pretty nasty. But the atomic physics give you stuff. So what I'm saying is these cross sections for bound free absorption are actually much more complicated, because you're taking the overlap integral of a bound state and a free state and getting those dipole moments. The thing is that you can, when you take account for the functional form of this, it's kind of like this goes as nu to the minus 3 instead of nu to the minus 4. You see the nu to the minus 4 out here? I'm not going to give you the whole breakdown of the derivation. It's just getting too beyond the scope of the class. But the point is that when you count for this, this sort of goes as a cube when you put that in there. I guess what I should say is this whole thing kind of approximates a nu naught over nu, or a nu over nu naught. Okay. I just wanted to show you that. And the difference is, if you plot up the real one versus the approximation one, if that's the real one, the approximation one looks a little bit different. I believe it peaks a little higher and it goes down a little faster. Something like that. Okay. So what I'm saying to you is, if you have good spectra and you're going to model the shape of the Balmer break, or say you want to model in a quasar spectrum the shape of a Lyman break, all right? See that difference there? You're going to get it wrong. You're going to get the wrong optical depth, or I should say, you're going to get the wrong column density. Okay, might be off by a factor of 5% or 10%. I don't know exactly what the number is going to be. But the point is, if you're going to do science, you want to do it right. So I want to show you the real formula and not the toy one. Because I really get upset about this. It's a little soapbox thing for me. That so many books, they regurgitate the same formulas over and over and over to people, and none of them provide any background to help you understand where it came from, or B, they give you the approximate formula, and they sometimes don't even tell you they are. And then people go off and try to do science with these wrong things, not knowing that really there's much more to it. Okay, so trying to show you the big league, not the minor league version of these things. So in the end, you have the cross section that gives you the break, okay? And then the cutoff frequency is given by this nice formula here. And for different ends, what n equals 2 is the Balmer, and different wavelength. And then this gives you where the n squared, n equals 2. Do this calculation, and you get the frequency at which the Balmer break happens. And so therefore, when I said at the beginning of the class that these goes as the cube, that was an approximation. If you really want to learn where all this stuff comes from, I studied all these papers. In fact, I did. Finally, we're there. take a seat for a minute and stop for a minute. And I want to ask if there's any questions about all that material that we've just talked about. If I gave you an absorption line profile now, could you obtain the proper column density from it? Okay. If I gave you an absorption profile or a spectrum that had a break in it, could you obtain the right column density directly from the spectrum, just using e to the minus tau? Okay. So I suppose it depends on whether you know how to write a least squares code or not. Something like that, right? Any other questions? You guys are like, nope. Okay. Well, there's your pause then. Okay. So I'm not going to go through as much detail on the multi-electron atoms because my book does actually kind of cover it in the same level of detail. And you've gotten the point. Overlap integrals, dipole approximation, you know. What I do want to say is these nice closed formulas that we have developed here, you can't get. Okay? You can't get them. To get a multi-electron atoms, what people do is they have to do numerical approximations. And it's called the Hardy-Frock method. Maybe you've heard of it. Okay. But basically, you have a much more complicated Hamiltonian, which is the sum over all the electrons, and the fact that the electrons are interacting through repulsion with each other. Okay? It's quite complicated. Right. And so basically, you break up this Hamiltonian into three versions of the Hamiltonian. I'm not going to go into the details, but one is basically a spherically symmetric model where you smear out the repulsion of the electrons and everything into a nice spherical model. And then you account for the point sources of the electrons themselves, and then you have the spin-orbit coupling effect. So you break the Hamiltonian, and then what you do is you solve numerically for these terms by making guess wave functions, making the wave function models, comparing that to the observations, tweaking them a little, and reiterating, okay, until it comes to equilibrium. That's called the Hardy-Frock method. Okay, and that's described here if you really care to know about it. You set up your initial guess, you keep iterating until you finally converge on a set of numerical wave functions. Okay. So you probably all heard of the Pauli exclusion principle. Okay, no electron bounded atom can have the same quantum numbers. We're going to be applying that. Okay, so if you have N, L, M sub L, and M sub S, so basically that would be for the M states for angular momentum and the spin state. Okay, now there's something else you have to deal with. It's called parity. It's going to be quite important. Basically, if you have even parity, you can replace minus r into the wave function and you get out the same wave function. If you have odd parity, then you get the negative back out of that wave function. Basically, you're saying if I switch the coordinate system, okay, I change the sign on the wave function. And the reason this is important is because we're going to find out with multi-electron atoms, there's going to be a selection effect that the parity is not going to be changing when a transition happens. And instead of you thinking the old-fashioned way, and I cannot emphasize it, I'm going to sit down to emphasize this. Instead of you thinking the old-fashioned way of the angular momentum state is really the angular momentum of the transitioning electron, we're going to make a new change. You're going to think of it differently. the atom itself, with all of its electrons, is in a total angular momentum state. And when a transition happens, maybe one electron transitions, that changes the angular momentum state of the entire atom. The selection rules apply to the entire atom. Okay? We say that the parity of the wave function of the entire atom cannot change. Or if we say the total spin state of the atom can't change. Or we might say the angular momentum of the atom can only change by 1 unit. We're not talking about the electron itself, we're talking about the angular momentum of the entire atom. And to get the angular momentum of the entire atom, you have to sum up all the angular momentum of all the electrons. When one changes, you have to account for the change of that one and redo all those sums to find out whether that transition is actually allowed or not. Am I making sense? That was the key thing right there to understanding the difference. Okay. So that brings us to the quantities that are written up in the notes. Can I borrow this for a second?
Yeah.
Where we define something called spectral notation. Okay, and we have the total angular momentum, the total spin, and the total orbital angular momentum of the electrons in the atom, and then the total spin. And then when you take the total spin, orbital and total spin, you get a total angular momentum of the atom. Okay, and the notation that we're going to use to describe the state of the atom is given by this, called the Russell-Saunders notation. The total orbital angular momentum is going to be a capital L. The total spin is going to be a capital S. And the total angular momentum is going to be a capital J. And we're going to say that the state of the atom is given by this. L, okay, where if L equals 0, we use a capital S. And if L equals 1, we're going to use a capital P. Do you see what I'm saying? And then we have 2s plus 1. So if the spin is equal to a half, 2 times a half is 1 plus 1. There would be a 2 up here. Okay, and then the total J down here. That way we describe in one simple piece of notation the entire state of the electron configuration of that atom. Okay, so for example, if I have L equals 1, S equals 1, and J equals 1, what's going to be my term notation? Okay, 0 is S, 1 is P, 2S plus 1, and that would be the state of my atom. You see what I'm getting at? So maybe you've seen this notation before. But what we're going to say then later is that the selection rules are going to apply to the total L, the total S, and the total J. So even though one electron might be doing a transition, the transitions that can happen are confined by the selection rules on the total quantities. Okay? Everybody with me on that? Thanks for letting me borrow the notes. How are these defined? Well, if you happen to know the angular momentum of each single electron, you sum them up and you get, this is a vector, you get the L vector. And if you know the spin, you get the sum, you get the capital S, this is the vector. And then J is the vector sum of L plus S. And then you have a capital M sub L and a capital M sub S. Remember, this M sub L, if you remember right, oh, here's the magnitudes. The magnitude of this vector is capital L times L plus 1 H bar. Do you remember that in the hydrogen atom, there was only one electron and the magnitude of L was equal to So now we have the magnitude of L. Same kind of thing. All right. And so the same thing applies with S and applies with J. Okay. And then you have the projections. And if you remember right, when you have L for a given electron, it can have minus L to L, M sub L's. Okay. So you get, and the same thing, these M sub F's are halves, either plus a half or minus a half. And you sum those up and you get the M sub F state. Okay. So how do you interpret these? Okay. Now, here's the thing. I'm not going to go into it, but summing the L's is actually a vector sum. So it actually gets tricky. It actually gets quite tricky, okay? Because little l can only change, they differ by 1. Anyway, that summation is explained in this paragraph right here, just FYI. I'm not going to go through it right now because we just don't have time to do everything, okay? Right. But your M sub L can go from minus L to L, just the same kind of thing, okay? Right, and then this is basically a description of the spin and how M sub S can go from minus S to S, okay, in units of 1. And this is how you interpret it. Okay. So you've got an atom, let's say, has 2 electrons in it. Okay? And electron 1 has L equals 1, and electron 2 has L equals 1. Okay, they're both in a p state, little p state. Okay? All right. So, M sub L, all right, you can have L1 vector pointing up and L2 vector, or sorry, L1 vector pointing down and L2 vector pointing up, which gives you the sum of L equals 0. And if case L equals 0, M sub L has to equal 0 too. Okay, so if their L's are misaligned, then the state of the atom is L equals 0, M equals 0, so that would be S. And then, depending on what the total spin was, okay, for, well, this is, I'm getting ahead of myself. Okay, this is, I think, the last thing I'm explaining today. The other option is that you can have, because of the projections of the vectors, you can have L1 here and L2 coming down at this angle and get an L1. Now notice that the magnitude of this vector is equal to L times L plus 1 h bar, square root of that. This is the other vector possibility that you can have. This gives you L equals 1 unit of h bar. And if L equals 1 unit of h bar, then ML is allowed to be either minus 1, 0, or plus 1. Okay. And then the other option is that the two can be aligned, okay, in which case L now is equal to 2, and if L equals 2, M sub L can be minus 2, minus 1, 0, plus 1, or plus 2. So just because you have a 2 electron atom, it could exist in many different L states. Well, 3 different L states, actually 5 different L states. It could either exist as a 0 L state, and it can exist 3 ways as an L equals 0 state, or, oh, I'm sorry, M sub L, I'm sorry. It can exist as an L equals 0 state, an L equal 1 state, and an L equal 2 state. Right? 2 electron atom, a total L of 0, 1, or 2. The M sub L can be 0, but it can be 0 3 different ways, etc. So this is the example of the vectors, okay? Here's the z-axis. This is the L equals 1, M L equals 1 example. So this is this example with M sub L equals plus 1. In that case, here's your plus 1 M sub L on the z-axis. Here's your L equal 1 vector. Here's your L1 and your L2. okay? The same triangle, it's just rotated because this is the L vector. Why is it rotated? Because this here is the projection plus 1, okay? And then, so your M sub L here, and your M sub L, and here's your capital L, here's your L1, your L2. Does everybody see that? And then what happens is that this precesses around the z-axis. Okay. So let's consider for the spin now what's going on. Let's again take the L equals 1 example. Okay? Take the L equals 1 example. Okay? So you can have both spin states up, in which case S is 1/2 plus 1/2 is a 1. Okay? And if that's the case, okay, yeah, so this is the example that the spin states are aligned together. Okay, right. So this is the possible L states. This is the example of L equals 1 with the projection ML equals plus 1. This is the example of L equals 1, okay, with the spins aligned. Spins are aligned. Got 2 electrons. It's an L equals 1 state. Spins are aligned. If spins are aligned, then S equals 1/2 plus 1/2, capital S equals 1. Everybody with me? So that's this example. Okay. In which case, S equals 1. In this case, you can have L misaligned with the spin with magnitude 1 and J equals 0. Or you can have L equals 1 up, spin it 1/2 at this angle, J equals 1. So this angle is defined by setting J equal to 1 because J has to be an integer value. So this angle is set by the fact that J has to be an integer value. Okay, in this case, okay, J equals 1, and L and S are aligned this way vectorially. Or you can have L equals 1 and S equal 1 aligned, in which case you get J equals 2. What is the spectral notation of that one? L equals 1, that's a P. S equals 1, 2S plus 1, that's a 3. J equals 0. That's a 3P0 state. Okay. What's this one? L equals 1, S equals 1. J equals 1. What's this one? Same thing. L equals 1, S equals 1, J equals 2. So, if this is where you get, this is see that these, you can see that these can take on so many different states because I've only given you one example. I've only given you the example of L equals 1, S equals 1, but in fact L could equal 0 or L could equal 2, and we could do a whole series of the spin possibilities in those and come up with a whole nother series of states that a 2-electron atom can be in. You see the complications now of all these possibilities? And you guys never say anything. Okay, so the interpretation, here's an example of J equals 1 with MJ equals 1, kind of the same idea. Here's your J vector, here's your S vector, here's your L vector, and then that processes around with your MJ projection of 1. Okay, if you had an MJ projection of 0, this would be turned on its side so that there was no projection of J, and then L would be down here and S would be down here. That would be an L projection of -1, okay, and an MJ projection of -1 or 0, and then you could have this thing tilted this way. You see what I'm saying? These are all these different vectorial possibilities. And so what I'm saying is even helium, a 2-electron atom, can exist in multiple angular momentum states of its spin, total spin, of its total orbital angular momentum, and of its total orbital plus spin angular momentum. And then what I'm going to tell you is that there are going to be selection rules that say, hey, if you start with helium in this state, it can only transition to these other states because of the selection rules. Imagine what it's like with iron. 26 electrons. Would you like to work out all of the possible states? That'd be a great homework assignment. Please work out all of the Russell-Saunders vector diagrams for iron. No thanks. Okay, be like, what's a PhD? All right, so I'm going to stop there, but I hope that I've given you a flavor for the notation and formalism of the multi-electron atom. Okay? All right. Thank you for your extra 5 minutes today. I appreciate that.